Presenter is online speaker. This is Professor Daniil Yurchenko, and so Professor Yurchenko is working in Southampton University, and the presentation title is Non-Smooth Dynamics of a Vibro-Impact Pair. Professor Yurchenko, please start your presentation.
Thank you, Professor Litek. Thank you, everyone. Let me share my screen. Can you hear me?
Yes, yes.
Okay. Can you see my screen now?
Yeah, yes.
Okay. Thank you very much for this nice invitation. And it's a pleasure to give a talk here. Unfortunately, I was not able to come due to some personal circumstances, but I hope to visit Chennai some other time. So what I'm going to talk about today is non-smooth dynamics of the vibro-impact pair, and this work has been supported by the EPSRC together with the United States NSF agencies. So what I'm going to do is briefly talk about the motivation of this work, and therefore I will start with the electrostatic energy harvesting explanations, and then I go to the concept of the vibro-impact pair, and then I show that actually under certain conditions, in this case, we can have a semi-analytical studies. And then I'll talk about important phenomena, which is the grazing bifurcations. And then I'll talk about why the grazing bifurcation is competing with the classical, for instance, period doubling bifurcations. And I also, if I have a time, to discuss a little bit the case of the asymmetric restitution coefficient in this particular system. So what I would like to start with is the basic understanding of the electrostatic energy harvesting. And I'm sure all of you probably even in school remember that in a simple capacitor case where you have two parallel plates on the right side, you can see there is a certain formula which you can use to find the Q, which is the charge, when you have a certain voltage applied to the sides of or to the plates of the capacitor. So this is the CV times equal to Q, where V is the voltage and the C is the capacitance. And typically in school, what we learn is that C is the constant. So if I provide you with V, you can tell me what Q is and vice versa. Now, in energy harvesting, people slightly change this understanding and they do slightly different things. So they remember that the capacitance actually is proportional to the two constants. One of them is the epsilon naught, which is the electric permittivity in vacuum. And then the other one is the electric permittivity of the material, which is between the plate. In case of the air, it's equal to 1. And then it's actually volume, which is the area times the thickness between the plates of the capacitor here, and Z is the distance between the plates. So what happens is if you assume that the voltage is constant and you start somehow changing the plates of the capacitor, you can either move them far away from each other and bring them closer, then you will be changing Z, which is the distance. So of course, the smaller the Z, the higher the capacitance. And on the other hand, what you can also do, if you imagine that these plates are not rigid and you can stretch them or change them in area, then you can imagine that the area will be changed and therefore the volume will be changed. So by doing the mechanical work over this kind of two plates, you can change the capacitance, and by changing this, you can see here from this very simple formula, change the charge or harvest energy. Now, there are two good things about this. One is that technically, we're talking about very high power density when you use this type of energy harvesting compared to typical electromagnetic or piezoelectric energy harvesting approaches. Now, the bad thing about this is that what you will need here is initial voltage. So basically, what you will do to harvest energy is the following. You will have a material in an unstretched position, okay? And then what you do is you stretch material so that you change the material area you can see from left to right, and also you can change the thickness of the material inside. And then what happens is you apply your voltage and let the material then be released from the force. So the material will go back, and then the capacitance will go change from the maximum to the minimum value. And then that's an extra voltage which you harvest, you can use to power batteries or to basically power sensors. Now, the other good thing about this is that because the electric permittivity of the air is very small, which is epsilon, what people decided to do is they decided to use dielectric materials inside of this or between these two plates. And those materials are called dielectric elastomers. And as you probably have heard about this, the good property about those polymers or dielectric elastomers is that they are very stretchy. So you can stretch them 3 to 500 times, 100%, or 3 to 5 times. And the other good thing about these materials is that in those materials, the epsilon is much, much, much higher than epsilon of the air. So sometimes in certain materials like acryl or very simple silicone, this may go to 5 and 10 instead of 1. When you add some doping, some specific parts into these materials, microparticles, it may go to up to 50 or even 100. That's why this is a very, very powerful way of harvesting energy. Now, as you can imagine, there are one issue which I have not talked about, and this issue is related to the electrode, because if you look at the top surface over here, you can see that I took the material and I start stretching this material in plane. But you can imagine that if I have regular electrodes, like for instance, copper or aluminum, they will not be able to be stretched for 2 or 300% or 500%. We're talking about maybe 5%. So what people do is they use the carbon nanotubes and they basically put it on top and the bottom of that dielectric elastomer. By doing that, you're basically creating a stretchable electrodes. And the reason for that is that because those carbon nanotubes are like very, very, very long hairs. They are about nanometers in diameter and about micrometers in length. So when you start stretching it, it's like spaghettis on your plate. They still will be overlapping, and this uniformity will provide you with the good surface charge when you apply voltage on top of this material. Now, as you can see, there are several ways of doing that. Stretching of this material, you can do it in plane, and the people do it either biaxial or multi-axial, basically, or uniform biaxial stretching, or you can do it in a three-dimensional way outside of the plane. So basically, in this case, one of the company developed an energy harvesting device from waves, and this is the device called oscillating water column, when basically the water comes and pushes the air up, and the air basically balloon the membrane. So the membrane, instead of being flat as a simple circle, will become a half a sphere. So it's kind of three-dimensional inflated balloon. Now I'm going to show you this small video, which you can see here. So if you look at this video, you will see that we have a device in the hands. So you have a small membrane in the frame. Oops, sorry, let me go back. You have a small membrane in a frame, and then we will start pushing this frame, this membrane in the frame, and you can look at that capacitance value here will grow up. So you can see here we push it, and then we go from 32 to, by pushing it, to about 168. So more than 5 times we increased the capacitance of this membrane by just pushing it out of plane. So this gave us kind of a, motivation for the work, which I'm going to talk about next. And basically, the motivation we kind of develop into the concept, which you can see here. So what you can see here is the cylindrical. You can imagine that this is just a cross section. So this is cylindrical capsule where you have a cavity in which the ball with the mass m small can travel freely, okay, left to right. And the two sides of this frame, which is on the left side here and on the right side here, are covered with the dielectric membrane. So this is the membrane, as we can see on the previous video. So you put those membranes, and every time when the ball hit the membranes, basically they get stretched out of plane. Okay, so the ball goes and hit left and goes here, hit to the right. And when they stretch out of plane, the capacitance is changed. And by doing that and applying voltage and taking voltage back, you can harvest energy. Now, there are a couple of things about the specifics of this device. So first of all, you can see that you cannot control the ball. So the capsule itself is excited by the external excitation F capital. And the ball technically, if it's in a horizontal direction, will not be excited until the ball hits the membrane, okay? Now, in the case of the slightly tilted device, as we can see here under angle beta, of course, ball will first start lying down on the left membrane or the bottom membrane. And then because of the oscillations, again, the ball will be hitting only one membrane. So it becomes like a bouncing ball. And then the next step, when the energy is good enough to overcome gravity, the ball will be traveling between the two membranes, impacting them both. Now, the equations of motion in this case are relatively simple, because what we would like to do is we assume there is no damping of friction between the capsule and the ball when it travels. And that assumption is very powerful because it allows us to basically later solve these equations of motion together. Now, the equation of motion for the capsule itself is very simple. It's just the capsule acceleration times the mass equal to external excitation when the ball doesn't hit the membranes. And then for the ball itself, the acceleration of the ball times the mass equal to mg times sine beta, because we have an angle at which the gravity acts. So if beta is equal to 0 in the horizontal case, then there is no gravity action in this case. And of course, when beta is equal to pi over 2 or 90 degrees, we will get a full gravity case. And what happens is, as I told you already, there is a condition of the impact. So what you will see technically is that when the ball hits one of the membranes, we use the instantaneous impact condition, which means that the velocity right after the impact equal to negative restitution coefficient times the velocity before impact. So we assume this happens instantaneously. But for the electrical side, because we need to know how much the capacitance have been changed, we use the full geometry of the impact, and then we can calculate impact as a non-instantaneous for the purpose of energy harvesting only. But I don't want to go into details of this. This work has been published, and you can find more details in the previous publication. So as you can imagine, this is the vibro-impact system, which has a lot of different kind of the bifurcations and types of the motion. So what we have done is that we can actually, you can see without the friction, combine these two equations, which are kind of a separate ones with respect to x capital, which is the capsule, and respect to x small, which is the ball, combine into one equation, which will be with respect to the z. And z, as you can see, is the relative motion. So that's basically the motion between the capsule and the ball. And you can see that this is a pretty straightforward equation because on the left side, we have a z double dot. On the right side, we have a term which is the constant. Remember, g bar is the gravity term, and then f of t is the excitation term. And we have also the condition of the impact, which happens when the ball hits one of the membranes. So because of these two, what we can do is we can integrate the motion of the ball between the capsule between the impacts. So you can find the z dot explicitly and z itself. And you can see here that we have a terms f1 and f2 capital, which are basically simple integrations of the first and second integral of the excitation function. And what I'm going to do now is I'm going to introduce one important parameter. This is kind of a non-dimensional distance d. And you can see that in this non-dimensional distance, it is proportional to the S, which is the physical distance between the membranes or physical distance of the cavity where the ball can travel. And A is the amplitude of the excitation. So you can see that you can change D with the given M, omega, and pi. We can change either by changing S or by changing A or by doing both. But I'll show you in some cases where we change both of these. Now, obviously, this is a very complicated type of the system, but fortunately, because we can solve this, analytically between the impacts, what we can do is we can develop several maps. So basically, in this notation, the map 1, P1, is where the ball goes from the bottom to the top. In P2, the ball goes from top to the bottom. In P3, the ball goes bottom to bottom, and then in P4, ball goes top to top. Basically, combining different types of those maps, you can develop different types of the motion. Of course, the higher the more complicated the motion, the more complicated the mathematics of that, and it's much more complicated to solve these equations because they cannot be unfortunately solved analytically. They have to be solved numerically. So these are exact equations, but which must be solved numerically because they are transcendent equations. So you cannot find them exactly analytically. So when we talk about the type of the motion, I will be referring to motion like 1-1 or 2-1 motion. It means that we have a one impact on the left membrane or the bottom membrane and one impact on the top membrane. So even in 1-1 motion, we can see different types of the motion. We can see, for instance, that the motion can be symmetric, as in this case. So you can see that the way the ball going up and down is absolutely the same, which is reflected in the time diagram here. You can have some type of the non-symmetric motion. You can see that the distance or the time covered is much shorter when you go from the top to the bottom than from the bottom to the top. You can have some certain kink over here. You see where the motion is kind of starting to change a little bit on the way from the bottom to the top. And you can even see not only asymmetric, but after period doubling, you can see 2T asymmetric motion, which is, you can see here that you have every other period is repeating. So this is a kind of a phase space representation and the time representation. But what I'm going to do is also show you the representation in terms of the bifurcation parameter D. So what we look at is we say, well, what if we start changing D, which is, remember, non-dimensional distance between the two membranes. So what type of the bifurcations we can observe here? And if you look here, there are three plots. One is for the relative velocity, another one is for the phase, and the last one is for the time between the impacts. So you can follow here and find the natural or eigen frequencies and determinant, and then using the value of those two basically variables, you can see what type of the bifurcations we're going to have. So you can see that this is symmetric motion because the velocity to the bottom is equal to the velocity to the top, you can see here. And also you can see that up to the point C1, the time going up and down will be identical the same. And then after C1, when you have a saddle node bifurcation, you can see that the time to go up will be higher than the time to go down. So basically using those diagrams, I'm gonna explain a couple of the in the next paragraphs, I'm gonna explain a couple of the other things. And this is the bifurcation diagram in the case of the asymmetric motion 1-1. So you can see that the velocity going from the top to the bottom is much higher. It's equal to 1 relative velocity compared to the velocity when you go from the top to the bottom. And of course, the time which takes here, you can clearly see is not the same. And then something happens after the bifurcation, but I don't want to stop on this. I would like to go to the next point. So one of the bifurcations which we cannot predict very well are so-called grazing bifurcation. So they are, although the ones which we predicted here were done by the linear analysis, we cannot predict by the linear analysis grazing bifurcation. And If you know what the grazing is, I'll just remind you that the grazing happens when basically the trajectory is tangential to the impact border, which means that basically the ball touches with the zero velocity the impacting surface and goes back. So you can see that this is the case here where we use G letter is the grazing bifurcation. And there is a certain condition for the grazing bifurcation. As I said, the velocity must be equal to zero when we touch the surface. So when we impose this condition, we can actually calculate different points when the grazing bifurcation happens. So if you go and look at the lots of publications on the vibro-impact dynamics, you can see that different publications tell you that there are different ways of the losing stability of the one type of the motion and getting to another type of the motion. So for example, this is the 4 diagram where you go from the motion 1-1, so that's one impact to the bottom and one impact to the top, which will be going to the 2-1 motion. You can see 2 impacts to the bottom and 1 to the top. And then it will go to the 3-1, which is the 3 impacts at the bottom and 1 to the top. So if we follow this for different values of the angle and the restitution coefficient and the values of A and S, depending on what we're changing, you can see that sometimes the stability is lost through the grazing bifurcation. So you can see letter G. But if you look carefully here, you can see that the velocity here is not equal to 0. So many of you can say, well, there is some contradictions. How does this happen? And in some cases, you can see if I go to the right figure, you can see that you have a stability loss here for the period doubling. And then this period doubling goes to the period doubling, which will end up with grazing again, which means 0 velocity. But we cannot see the 0 velocity. And I'll explain in a couple of minutes what's going on here. And then you can see that after period doubling, you go grazing. And then in 2 other cases, you can see that you don't see grazing at all, or you see period doubling, which end up with grazing, where grazing goes to 0. So what happens is there are lots of different cases. And the question is, so when grazing happens and when the period doubling happens, it was not clear. And we decided to figure this out for ourselves. So for the further kind of discussion, I'm going to show you a couple of the things. And when we what we do is we introduce 2 extra things. So usually we know what is the period doubling. We can identify it through the linear stability analysis. We know what is the grazing, and we assume that there are different types of the grazing, but this is the grazing which we can observe. And what we go is introduce the grazing bar, G bar, and PD bar. So this is a PD bar and G bar we call ghost grazing and ghost period doubling. And they are ghost because they are there, but they are not visible to us. So the question is, how do we know that they are there and what will appear first? So what we did then is we built the following diagram. So this is a very important diagram. I'm going to stop on it a little bit longer. So if you go here, you can see that on the top row, you can see this is diagram for losing the 1-1 motion or stability of 1-1. So you're going from 1-1 to 2-1 motion when D is decreasing. And in this case, you go from 2-1 to 3-1 motion, or maybe 2-2 in this particular case, there is also 2-2 motion. Again, for D is decreasing. And there are 2 different things. On the left row, on the left column, you can see we're reducing S, which is meaning that we physically reduce the distance between the membrane. On the right side, we do opposite. We also decrease D, but we do that with increasing A. Remember, because A is inversely proportional to D. So in this case, we pump a little bit more energy into the system. In this case, we don't pump any energy. We just reduce the physical size. Now, what you can see here in blue are the period doubling bifurcations, which happen at a certain value of D if you start crossing it from top to the bottom for any given value of the restitution coefficient and any given value of the angle. So what happens is, and the blue and the green one is the basically grazing bifurcation. So what happens, for instance, if you take very, very large values of R, let's say 0.8, and you take any of the angle, when you start reducing your D, you will first go through the period doubling bifurcation, which means that the grazing bifurcation will not be visible. So that becomes a ghost bifurcation. However, if we increase or decrease the angle, you can see here, and then if we take very low value of R, you can see that for some cases, for instance, for this case, the green one will happen first. So the grazing bifurcation will take place first, and the period doubling bifurcation, although it's there, it will not be visible to us, okay? So now you can see that basically in both cases, if you look at the first row and the second row, we can see that the grazing bifurcation can be observed for relatively small values of R, okay? And basically very small values of angles. You can see that these angles are pi over 18, pi over 6, and so on. And then you can see that the period doubling bifurcation can be more often observed for the higher values of R and the higher values of angles here. Now you can see also that when you increase A, basically, you know, you in many cases will observe only the period doubling bifurcation. So the grazing bifurcations will not happen in a case going from 1-1 to 2-1. Now, when you go from the 2-1 to 3-1, the situation a little bit changes here, and you can see that in more cases, you will see that the green line for the corresponding angle is above the blue line, which means that the grazing will happen first, and then we will not be able to see the period doubling bifurcation. So if this is clear, I would like to go and just demonstrate a couple of the results here. So if we go, for instance, at this particular case, we'll look at the pi over 9 and R equal to 0.3, so we will be somewhere around this point. So you can see that we have a pure grazing bifurcation when we lose stability of 1-1 motion to 2-1 motion. So it goes through the grazing. And then when we lose the stability of the 2-1 to 3-1 motion, it also goes through the grazing. So in both cases, we observe grazing. And I'm not talking about this particular point where the velocity is not zero. I will speak about this on my next slide. Now, in this case, when we move to the right, we can see that in those points, in both cases, the period doubling bifurcation will happen first. So although the grazing is there, it will be ghost. So we will not be able to observe this grazing. Well, very similar here when we start increasing A, you can see that in many cases here, or in most of the cases, you will have a period doubling going on here. But in the case of the 2-1 to 3-1 motion, you can observe the grazing bifurcation. So you can see here there is a grazing bifurcation. Okay, so what I'm going to do now is I'm going to go back to one of the slides, which I show you as a motivation in the beginning, where there were 4 different types of the ways going from one type of the motion to another one, and I go slowly over this step by step. So basically, we take the values along this line. So we take the values of the pi over 6 and R equal to 0.3. So you can see here the period doubling bifurcation will happen first, and when we lose 2-1 to 3-1, the grazing will be happening. So if you look at this diagram, you can see the following. So you can see that we have a stable 1-1 motion up to the certain value of this D. And then what happens is, as we know, the 1-1 motion will be lost and unstable, and we go through the period doubling bifurcation as predicted by this diagram. So we'll get the 1-1 motion, which is the 1 impact per each side, 1 left and 1 right membrane, 2T motion. And then what happens here is we go through the kind of, we call it transition grazing, because this is basically almost like chaotic motion, and some of the trajectories will basically touch the boundary with the zero velocity, but others will not. So you get this type of the motion. And you can see here that the end of this motion is the fold bifurcation point. So basically over here, there are another solution appears. And when you travel to the left, what happens is you can see that actually when we were not able to see this zero velocity for the grazing, what actually happens is it is over there, and we can find it, as you can see it in a red color in this plot. But because it is on an unstable branch, these two pink ones are unstable branches, the solution basically jumps earlier to the 2-1 motion, and therefore we don't see this grazing, but we were able to identify it for our analytical solution. So this type of the grazing you can see on the top, I mark with the bar because we call it ghost grazing. And then, of course, if you go to the next step, then you can see just a classical grazing bifurcation. So you can see that velocity goes to 0 first, and then we have another branch which give you raise to the 3-1 motion. Okay, so basically, if you start now plotting what's going on for the decreasing value of d, you can see that the motion is very complicated in terms of what is the pattern of the stability of one motion or the stability loss of one motion going to another motion. So in this particular case, for pi over 3, you can see that when we start decreasing d, everywhere we will go first through the period doubling bifurcation, and then we will go through the period doubling / grazing, so which means that end of the period doubling will be through the grazing. And then depending on the values of r, what happens is we will either go through the, as you can see here, grazing, which goes from 2-1 to 3-1 motion, or on the right side, when the r is big, we will go through another period doubling from 2-1 to 3-1. However, this pattern may change, as you can see on the right side. So for smaller angle, you will have already variety of options here. So for instance, when the r is very small, you will go from 1-1 to 2-1 through the grazing here, and then through the grazing again here. If you go slightly to the right, the 1-1 will go to 2-1 through grazing, but then from 2-1 to 3-1, it will go through the period doubling. Okay, which is kind of a ghost period doubling. So you will be jumping now to period doubling 2-1 to 3-1 here. And then on this case, you will go through the classical period doubling, and the grazing will not be visible. It will be ghost grazing here. So what we've done, basically, we show that there are 4 different types of the ways going or losing the stability, and one of them is through the classical grazing, where you just add another impact per period. Another one is through the invisible grazing, where basically you have a grazing, ghost grazing on an unstable branch. Another one through the period doubling, which leads to period doubling grazing, and finally through the kind of a transient grazing, as you could see when the fault bifurcation happens. And to finish this, I would like to spend 1 more minute on this diagram. So basically, what we've done next is let's consider that the left and the right membrane have a different restitution coefficient. So you can see that the top membrane here has a restitution coefficient of 0.5, and in this row it's 0.3. And this is the left. You can see that the angle here is pi over 6 in the left column, and on the right column is pi over 2. And what we're trying to do here is change restitution coefficient of the bottom and see how this influences the results. So all the previous presentation was about this case when RB over RT was 1. So we were on this line. But as you can see here now, first of all, if you go through the analysis, and you will see that there are 2 different types of the period 1 motion. So you have a 1-1 motion on the left side, and then there is, you can see kind of a separation border, and 1-1 motion on the right side. So depending on the angle and depending on the restitution coefficient condition, you can see that the motion stability can go through the different pattern of losing the stability. So you can see in the first case, mostly the stability loss happens here through the period doubling. So you go to 1-1 to T, and then you go through the grazing, except this part over here. Whereas, for instance, on the right side, when you increase the angle, there will be a part where you go through the grazing here, very little part. But if you start changing the RB, you can go through the grazing to the basically 1-2 motion. And in this case, you can see that this is on the left side, 1-1 motion. One type of the 1-1 motion loses stability through the period doubling, whereas another one, depending on the value, relative value of the bottom and the top coefficient, it may be either through the period doubling or through the grazing. And the background here is the amount of energy we kind of gain every time, depending on all those values of the parameter. So in conclusions, I would like to say that we have shown that there is some competition between the classical bifurcation, which is period doubling and fold, and also the grazing bifurcation. We identified the 4 different ways of the stability loss, especially through the grazing bifurcation. We also have shown effects of the different type of the motion, and we considered, we didn't consider the TED here, but we considered different types of the restitution coefficient. I would like to thank my co-authors, Professor Rachel Kuski from Georgia Tech and Professor Larissa Serdyukova from Leicester University. And I would like also to acknowledge the support of the NSF and EPSRC on this project. And most of those works I reported have been already published. So if you have any questions, I'm happy to ask to answer them. Thank you very much.
Oh, thank you very much. Yes, so there is some space for question. Yeah. Is there any question? Yeah.
Yeah, I was told it's a 35 minutes presentation, so I tried to be within time.
Yeah. Okay, so this was very interesting presentation. So I have the first question, and my question is about this. You discussed bifurcations, but in the beginning, your motivation is that you are going to use this system for energy harvesting. So
yes.
So the problem is that probably grazing is not useful for energy harvesting because you know this is only some touching to the membrane, and how you estimate this energy from different regions of these diagrams which you obtained. Yeah.
Yes, exactly. So first of all, thank you for this question. Yes, the grazing is not desirable because when you have a grazing, the velocity is 0 or very, very small. So basically it doesn't give you any impact, and that means that it doesn't deform the membrane, so the power will be very low. But when we know where the grazing is, then we can avoid these regions. So the most important part is to avoid the regions where the grazing is. Now, if you look at this diagram is also valid for RB and R1 equal to 1. So they are basically the same here. The ratio is equal to 1. So if you look at this region, you can see that most preferable region for energy harvesting is 1-1 region, because the more energy is gained when you have a strong impact, one impact per period per each membrane. So therefore, if you look at the graphs here, for example, you can see that this is the most desirable region where you have D. So as long as we know where the grazing may start, or where we may jump to another solution, we want to be away from this region. So for a given amplitude, I can basically design the angle, and I can design the length of my membrane, of my capsule, so that the membranes are hit in the 1-1 motion. So the 1-1 motion is stable.
Okay, thank you. Any other question?